Welcome to Chapter 7, the mole and chemical composition. You're going to love Chapter 7. You'll need a periodic table and a calculator throughout most of Chapter 7. So if you don't have that, you might want to pause the video and find yourself a calculator and your favorite periodic table. Now, moles might be fuzzy little creatures that dig around in the dirt, but in chemistry they are very, very important. The mole is a unit. It's used to measure a quantity of atoms or molecules or whatever the particle might be. It's used kind of like the word dozen. Well, a dozen is a unit. It means that you have 12 of something. You could have a dozen donuts. You could have a dozen eggs. You could have a dozen atoms or molecules. But 12 atoms or molecules isn't enough that I could actually measure it in the lab. Atoms and molecules are ridiculously tiny. So this mole is a unit that represents an extremely large amount of atoms or molecules, whatever the particle might be. Because these atoms or molecules are crazy tiny, we need a gigantic unit that can quickly and easily measure a large quantity. It's called the mole. It stands for a few more than 12. 6.02 times 10 to the 23rd particles. Now, obviously the number is large, 10 to the positive 23rd. If I wanted to take this out of scientific notation, I would be moving my decimal spot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and however many spaces that is until I hit 23. Whoa! It's like a 6 with 23 zeros behind it. What would you even call that number? Like million, gazillion? I don't know what comes after that. Billions and billions and billions. This number is so large that it's really hard to even comprehend how many particles are in a mole. The number is so crazy, crazy large because on the flip side, atoms and molecules are so crazy, crazy, crazy tiny that we need this many of them before we actually have a measurable quantity that I can work with in the lab. It's crazy, crazy large. We call this number Avogadro's number. It was named after a guy named Amedeo Avogadro, who was kind of the founder of this mole concept. If we try to really comprehend how large this number is, think about this. Would you want a mole of pennies? I mean, it's just a penny, right? I don't know. I guess I would take it. If you had a mole of pennies and you wanted to convert that to dollars, you'd take your 6.02 times 10 to the 23rd pennies, and we divide by 100. There's 100 pennies in a dollar, and that doesn't really do me a lot of good. 6.02 times 10 to the 21st dollars. But again, this number is so large, like, I mean, I can't count that many dollars. I guess, yeah, I would take that. So now put this in perspective. Starting with a mole of pennies, we converted it to dollars. It's still astronomically large. What if we distributed that mole of pennies amongst every single person on the face of the earth? Assuming that maybe there's 7 billion people. I don't know the current world population. How much money would each person receive? I don't know. Let's figure it out. So let's start with our dollars. Let's say we had 6.02 times 10 to the 21st dollars. And we divide that by 7 billion people. Okay, so 7,000. Come back to me. It's thinking. Here we go. 1,000 million billion people. Okay, so I plug this in my calculator and I get, yikes, it's like 6 times 10 to the 11th. That's dollars per person. And again, I know it's a large number, but really, how large is that? Think about this. This 7 billion. If I put that in scientific notation, it's like 7 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th. That's 7 billion. This is even larger. If you started with just a mole of pennies, every person on the face of this earth would be more than a billionaire. Would you take a mole of pennies? You betcha I would. Holy cats, that's a lot of money. This calculation is really just trying to put in perspective how large a mole really is. This number, 6.02 times 10 to the 23rd, is ridiculously large because we need a way of counting and measuring something that is ridiculously small. So on the flip side, it's really hard to even fathom how small an atom is. You need that many of them, 6.02 times 10 to the 23rd atoms, before you really have a measurable quantity. Okay, so cool. How are we ever going to use this number? It's something called molar mass. Molar mass is just that. It's the mass of a mole. How do you find the mass of a mole of particles? You look on your periodic table. Now, back in the day, we were using molar masses. We were using the mass on the periodic table, but we called them atomic mass. Atomic mass. We were looking at the numbers on the periodic table. Let's say I was looking at carbon. We said carbon was 12, and we used the unit AMU. 12 AMUs, atomic mass units. What that really meant was that there were 6 positive protons and 6 neutral neutrons. And the mass of the electron was pretty insignificant. In AMUs, you're looking at the mass of the nucleus, the number of protons and neutrons. We cannot measure protons and neutrons in the lab. We cannot measure in AMUs in the lab. But I can measure in grams. So we want a unit that lets us measure in grams in the lab. That's molar mass. Okay, so you still go to your periodic table, you look up the mass of carbon. Carbon is 12, but this time we call it grams per mole. Molar mass, grams per mole. This is the mass of 6.02 times 10 to the 23rd atoms of copper. It's the mass in grams of a mole. And now again, 12 grams is something that I could measure in the lab. I could put 12 grams of carbon on an electronic balance. But we just have to be aware that the 12 grams, that is by far not the mass of one carbon atom. That's the mass of a mole of carbon atoms. 6.02 times 10 to the 23rd carbon atoms. That's a lot of carbon atoms. But yeah, this is a number that I could measure. And so to find molar masses, all you need is your periodic table. We just look up the mass on the periodic table. So for example, copper, 63.55. If I want to use that as grams, a number that I can put on the electronic balance, I can measure 63.55 grams of copper in the lab. But then again, we just have to be aware that that is not the mass of one copper atom. That is the mass per mole. the molar mass, which, by the way, the abbreviation for mole is MOL. What a shortcut, huh? You drop the E. 1 mole of copper atoms, 6.02 times 10 to the 23rd copper atoms would have a mass of 63.55 grams. I can look up sodium. 22.99 grams per mole. Iron. 55.85 grams per mole. Easy. Now again, different periodic tables might have different number of decimal spots. In general, I usually say leave at least 2. Leave at least 2 decimal spots on your molar masses. And so again, here's kind of the gist of this. These masses, these are all 6.02 times 10 to the 23rd particles. These quantities, if I were to go in the lab and measure 63.55 grams of copper, about 23 grams of sodium, 55.85 grams of iron, I would be measuring the same number of particles. The same number of particles. 6.02 times 10 to the 23rd particles, to be exact. That's a lot of particles. Their masses are different. And that goes back to the atomic structure. On an atomic level, oh yeah, copper atoms are larger. There's more protons and there's more neutrons. If you multiply that extra mass by 6.02 times 10 to the 23rd, it's a measurable quantity in the lab. See, this concept of a mole, it's a way of counting particles in the lab by using mass, because there's no way that I can count individual atoms or molecules. They're just way too tiny. But if we use their molar masses on the periodic table, indirectly, if I measure that amount in grams, I do know how many atoms are in the sample.